Good morning and good afternoon, and welcome to this final video on Newton's three laws. Again, the context here are for 6th grade STEM classes, but if you're in a science class, great. If you're in an engineering class for the 6th grade, okay, these rules apply. And of course, mathematics, we had a lesson on force, so that covers that. So let's cover a couple of different things, and let's put everything that we've learned so far together and see what we have learned. All right, so we learned that the first law from Newton says that objects resist changes in motion. All right, an object in rest stays at rest. An object at motion wants to stay in motion unless other forces act upon that. All righty. We also learned that force causes acceleration based on mass, and then usually the third law, forces come in pairs. So I got a little demonstration here that will show all three working. What I have, if we're looking at the screen, so look at my screen on the lower right-hand side, I have a coffee mug, and it's branded with, Florida Gateway College. That was before they became known as, that was after they became known as Florida Gateway College. They're still FGC. They used to be called Lake City Community College. So what I'm going to do is I'm going to take this cup, and I need to hold it in one hand. I'm going to put an index card right on top. And then I got a stack of light magnets here. Now, there's nothing magnetized in here. There's no metal. All righty, there's nothing metal in the ceramic. So we're not focused on magnetism. I'm just using these because they have a little bit more weight to them. And what I'm going to do is I'm going to put the magnets right there. All righty. Now, if you're looking at this saying, okay, I see it. There's a little bit of a curvature in the center indicating the weight. All right. Objects resist changes in motion. All right, so what I'm going to do here in a moment is I'm going to flick the card, and I'm going to flick it towards the camera, and we're going to observe what happens. And I'm going to kind of tilt it slightly. Oops, can't tilt it too much, all right, or else the thing wants to move forward on me. So here we go, and oops. I'm not flicking it right. Let's try it one more time. Let's line it up, and let's flick it correctly there. All right, tilt and flick. All right, so do we see what happened there? All right, when I flicked the card, the magnet that was stationary, all right, stayed. Why? Because it resisted the motion, the inertia at rest. It wanted to stay at rest. Then, force. Force causes acceleration based off of mass. In other words, this index card doesn't weigh a whole lot. There was more force applied by my finger, okay, when it flicked the card, all righty, and it caused the acceleration of the card, quick acceleration, matching the speed of my finger. We learned that force equals mass times acceleration, or force equals mass times, we learned that equation, all right? And then finally, force comes in pairs, okay? In other words, for every action, there is an equal and opposite reaction. When I flicked the card, it came from the opposite direction, right? I flicked from behind the card. Why? Because I wanted the card to move forward. All right, that's how they all work together. Pretty easy there. But there's some other examples that we could use as well. Example, we just saw the magnet resting on the card. It's kind of like a book resting on a table, right? Gravity is acting as a force on the book. That table is suspending that and holding it from hitting the ground or the floor, and is countering the force of gravity. Okay, pretty easy there. And I would say on that table, if it's sturdy enough, it could counter a lot more forces than just, of that book. It would take multiple books to weigh that table down, right? Now, we could also think about a ball rolling down a hill. There's multiple forces in there, right? You have the force of course, gravity, and now that ball is rolling down a slope, okay, and you're able to see that ball slowly gain speed until it can reach the fastest it can reach based off of the size of that slope, the weight, friction, so on and so forth, right? So force equals mass and then times acceleration squared, or mass time, F equals ma. There you go. And then, of course, a car accelerating, okay? This kind of says for every action, there is an equal and opposite reaction. In other words, the more power that's applied to the wheels of the car, all right, the more that car is going to accelerate. And you're going to feel that in your body because your body's being kind of pushed back. And then once you get to cruising speed, you can kind of feel that neutral balance and what's going on with the vehicle itself. So why is it we notice one force more? Well, if you notice, probably what you would think is, hey, on here where I have the magnet on the cup, what I notice is, well, it being suspended. We don't think about the other forces that are being acted upon it. We don't think, okay, gravity. Okay, there's something being suspended and holding it in the air from the floor. And that's what's happening. I'm sitting on a chair. I'm residing on the chair. My feet, although they are touching the floor and not suspending me, they're just keeping me balanced. There's a torso and an arm, right? So those are the things that we can see, the observable effects. We see that there's a role for force in mass acceleration. Of course, we can measure that in newtons, and we can measure that in pounds of force, okay? And then, of course, there's times where both sides are obvious. In other words, when I flick the card, okay? But there's other times where the force seems dominant. Like if you're in a vehicle, you don't think maybe, hey, that engine is spinning, and that spinning motion is being transferred into what they call an axle, and that power is being put to the tires, and those tires are spinning, causing the car to move forward. We only may think about acceleration unless we're taking a deep dive. So sometimes one force may seem dominant, like, again, something resting on a table, it may seem only gravity is working on it, or it may even seem like it is stationary. Is it stationary? I don't think so, because when we consider the rotation of the Earth, when we consider the rotation of the Earth around the sun, and then when we consider whatever our solar system is spinning around within the galaxy itself, okay, and then there's the universe to consider, wherever there's a spinning point, if there is one, so on and so forth, right? So one force might seem dominant, but there might be other forces at play. So that brings me to the end of these presentations. I hope you have gathered something from these, something substantial, and I hope that you can take something forward as you continue your work in STEM and as you continue to observe the life around you.